Hello, fellow AI enthusiasts and admirers of technological wonders. I'm Lisa, and I hope you're doing well. If you haven't watched the first part of our conversation yet, titled AI Extraordinary, Amazing Insights of Artificial Intelligence on JouleThiefCircuit, you can find the link at the top of the screen. I highly recommend watching the video for valuable insights. Today, we extend our dialogue with AI, delving into diverse and fascinating topics, and casting a spotlight on the enchanting realm of electronic circuits. This marks the subsequent installment of our thrilling journey into artificial intelligence. Our objective is to foster a captivating conversation with AI, unraveling the unique opinions it contributes to the subject. On the video screen, you'll encounter a thought-provoking question directed to AI, and we keenly await its enlightening responses. I'm genuinely thrilled to observe the AI's distinctive opinions and perspectives unfold in response to these engaging questions. And here's a special invitation for you. If you enjoy this video, please subscribe to our channel, hit the bell icon for timely updates, and share your thoughts in the comments. Feel free to propose topics you'd like us to explore in future dialogues with AI. Your participation adds a unique dimension to this experience. Let's dive into the exploration without further ado, initiating a captivating discussion centered around the Joule Thief circuit. First and foremost, we welcome you.
Thank you. And I am happy to share my opinions with you in this dialogue segment. I expect our discussions to be enjoyable, and I am grateful for the warm welcome. Thank you for having me.
Thank you. Let's begin with the first question. Can a Joule Thief circuit power a small electronic device using energy extracted from a banana or other fruits?
What a delightful start. Creating a Joule Thief circuit to extract energy from a banana or other fruits is theoretically possible, but it comes with several challenges. Fruits contain electrolytes, and the acidic or alkaline nature of the fruit can act as an electrolyte solution. Here's a simplified explanation of how it might work. Fruit as electrolyte. The fruit, acting as an electrolyte, allows ions to flow between two electrodes. Electrodes, two different metals, like copper and zinc, can act as electrodes, creating a potential difference. Joule Thief circuit. The Joule Thief circuit can step up the low voltage generated by the fruit to a level sufficient to power a small electronic device. However, there are significant challenges. Low voltage. Fruits typically produce a very low voltage, which might not be enough to power electronic devices efficiently. Interference. The organic nature of fruits can introduce impurities, affecting the efficiency and stability of the circuit. Limited power. Extracting energy from fruits may generate very limited power, suitable only for small and low-power devices. Chemical reactions. Over time, chemical reactions with the electrodes and fruit could affect the circuit's performance. While it's a fascinating concept, practical implementations would require careful consideration of these challenges, and might be more of an educational or experimental project, rather than a reliable power source for everyday devices.
I commend your insightful answer. Now, let's dive into further details. Is the Joule Thief circuit designed to increase the voltage or the current?
Great question. The primary purpose of the Joule Thief circuit is to increase the voltage. It is specifically designed to boost a low input voltage from a power source, such as a single-cell battery, to a higher output voltage. The circuit achieves this voltage increase through the principles of energy storage and transfer in the inductor, allowing it to power devices that require a higher voltage than the power source initially provides. The main goal is efficiently converting low input voltage to a higher output voltage.
Does the Joule Thief circuit alter the intensity of the original power source's current, or is the current output the same as the source?
What an excellent question. Understanding the impact of the Joule Thief circuit on the current from the power source is crucial. In a Joule Thief circuit, the current drawn from the power source is altered. The circuit's operation involves storing energy in the inductor during the transistor's off state and releasing it to the load when the transistor is on. This process results in a pulsed or oscillating current, and the average current drawn from the source is typically lower than the peak current in the oscillations. Therefore, while the circuit increases the voltage, it does so at the expense of altering the current waveform. However, it's worth noting that the circuit's efficiency plays a role in how effectively it utilizes the available current from the power source.
Could you provide further details?
Certainly, let's delve into further details. Understanding the impact of the Joule Thief circuit on the current from the power source is crucial for a comprehensive view of its operation. The circuit modifies the current drawn from the power source as an integral part of its functioning. The operational sequence involves two main states: the transistor's off state and on state. During the transistor's off state, energy is stored in the inductor. Subsequently, when the transistor is in the on state, the stored energy is released to power the load. This cyclical process results in a pulsed or oscillating current waveform. The noteworthy characteristic is that the average current drawn from the power source is typically lower than the peak current observed in the oscillations. This alteration in the current waveform is a consequence of the circuit's energy storage and transfer mechanism. While the primary objective of the Joule Thief circuit is to increase the voltage supplied to the load, this enhancement comes with a trade-off in the alteration of the current waveform. The circuit achieves voltage boosting by efficiently utilizing the energy stored in the inductor, leading to a modified current pattern. It's essential to emphasize that the efficiency of the Joule Thief circuit is a critical factor. The efficiency influences how effectively the circuit utilizes the available current from the power source. A higher efficiency ensures that a greater portion of the available current contributes to the voltage increase, minimizing losses and optimizing the circuit's overall performance.
Your response motivates us to strive for innovation. Let us know your opinions on can the design, components, or both of the Joule Thief circuit be modified to increase the current?
What an insightful question. Exploring modifications to the Joule Thief circuit to enhance current is a fascinating idea. However, it's important to note that the Joule Thief circuit is inherently designed to increase voltage rather than current. The circuit operates by storing energy in the inductor during the transistor's off state and releasing it to the load, resulting in a voltage boost. Modifying the circuit for a significant increase in current would require substantial changes to its fundamental principles, potentially transforming it into a different circuit altogether. If the primary goal is to obtain higher current levels, other circuit configurations, such as a current booster or amplifier, might be more suitable for the intended purpose.
Your keen comparative perspective takes the spotlight. How does the Joule Thief circuit differ from a boost converter?
The Joule Thief circuit and a boost converter are both electronic circuits used to increase the voltage of a power source. However, they differ in their design, operating principles, and applications. Design: the Joule Thief circuit is a relatively simple circuit that typically consists of an inductor, a transistor, a feedback winding, and a resistor. It is designed to efficiently extract energy from a low-voltage power source, such as a single-cell battery, and boost the voltage to power a load, often in lead. A boost converter, on the other hand, is a more complex circuit that typically includes an inductor, a switch, usually a transistor, a diode, and a capacitor. It is designed to convert a lower voltage input to a higher voltage output, and can handle a wider range of power requirements. Operating principle. The Joule Thief circuit operates by utilizing the energy stored in the inductor during the transistor's off state. When the transistor is switched off, the collapsing magnetic field in the inductor generates a voltage spike that is applied to the load, boosting the voltage. This process allows efficient energy transfer, even when the power source voltage is very low. A boost converter, on the other hand, operates by periodically storing energy in the inductor during the switch on state, and releasing it to the output during the switch off state. This continuous energy transfer cycle allows the boost converter to step up the voltage of the power source. Applications. The Joule Thief circuit is commonly used in low-power applications, such as driving LEDs from a single-cell battery or other low-voltage power sources. It is particularly useful when the power source voltage is close to the LED's forward voltage, as it can efficiently extract the remaining energy from the battery. A boost converter is more versatile and finds applications in a wide range of devices and systems where higher voltage levels are required. It is commonly used in power supplies, battery chargers, DC-DC converters, and other applications that involve voltage stepping up. In summary, the Joule Thief circuit is a simpler circuit used for low-power applications and operates by extracting energy from a low-voltage power source. A boost converter is a more complex circuit used for a wider range of applications, providing higher voltage conversion capabilities.
We become fascinated by the possibilities. We venture into the realm of higher power. How can a Joule Thief circuit be used in high-power applications?
It is not recommended to use a Joule Thief circuit in high-power applications, as it is designed to operate at low power levels. Attempting to use it in high-power applications can cause damage to the circuit and components, and may pose a safety risk. It is important to choose the appropriate circuit for the specific application based on its power requirements.
Now we come to an important question. Is the Joule Thief circuit considered a type of energy harvesting circuit?
No. A Joule Thief circuit is a specific type of circuit that is primarily used for voltage boosting, and is not typically associated with energy harvesting circuits. Energy harvesting circuits, on the other hand, are designed to capture and convert ambient energy from the environment into usable electrical energy. These circuits can utilize various sources such as solar radiation, thermal gradients, vibrations, electromagnetic waves, or RF signals. The goal of energy harvesting circuits is to efficiently capture and store energy from these sources to power electronic devices or charge batteries. While a Joule Thief circuit can potentially be used as part of an energy harvesting system to boost the low voltage output from an energy source, it is just one component or subsystem within a larger energy harvesting circuit. The energy harvesting circuit would include additional components such as energy storage elements, power management circuitry, and possibly specialized interfaces for the specific energy source being harvested. Therefore, while a Joule Thief circuit can be integrated into an energy harvesting system to enhance voltage levels, it is not synonymous with energy harvesting circuits as a whole.
In the last question, we turn our attention to innovation. Have there been recent advancements in circuit design beyond the traditional Joule Thief, specifically designed to enhance energy extraction and boost efficiency?
Certainly, your question touches upon the exploration of recent advancements in low-power applications and circuit topologies. Here's a possible response. In the realm of low-power applications, there has indeed been a continuous drive to push the boundaries of energy extraction and enhance overall efficiency. Recent advancements have led to the development of innovative circuit topologies, that go beyond the traditional Joule Thief. One notable example is the emergence of multi-stage energy harvesting circuits. These circuits feature multiple energy harvesting stages, each optimized for specific voltage ranges, allowing them to efficiently extract energy from sources with varying power levels. By cascading these stages, the circuit can adapt to dynamic environmental conditions, maximizing energy extraction. Furthermore, researchers have been exploring the integration of advanced control algorithms and energy management systems into low-power circuits. These intelligent systems dynamically adjust the circuit parameters based on real-time conditions, optimizing performance and adapting to fluctuations in the energy source. Additionally, advancements in material science have contributed to the development of novel energy harvesting materials, with improved conversion efficiencies. Integration of these materials into circuit designs has shown promise in enhancing the overall energy extraction capabilities, especially in scenarios with limited power availability.
In conclusion, I want to thank the AI for sharing its unique perspective and its opinions on the Joule Thief circuit. These insightful answers have made this conversation genuinely exceptional. We're excited about the upcoming videos, promising more engaging dialogues with the AI. And speaking of the upcoming video, get ready for an incredible journey with the opinion of artificial intelligence about a wonderful Indian movie. It's a topic that will captivate your imagination. So stay tuned for another exceptional addition to our video series. If you enjoyed this video, please subscribe and hit the notification bell for future updates. Your thoughts and topic suggestions are always welcome in the comments. Thank you for watching, stay happy, and keep exploring the wonders of artificial intelligence. See you in the following video.